Hi and welcome. This is a small, let's say, recording of a small demo held at the DEBS conference on how to benchmark NebulaStream. First of all, I want to highlight that this recording is in a similar-ish form, also written down as a guide on our documentation website, so on docs.nebula.stream. Here on the left, under development guide, there's this guide on how to benchmark NebulaStream, and we'll roughly follow along this guide. If you want to run this, take your time, read it, feel free. We will, as done at the DEBS, we will now use a pre-built Docker image of NebulaStream with a small benchmarking utility to run a few benchmarks, look at the results, and hint at the research that, let's say, is behind these results. And first of all, we will pull the image. So it's DEBS 2024. I already have that image installed. In the current directory here, we have a few files. These YAML files describe benchmarks. To run them, we run the Docker container, and also we mount the current directory in the bench directory. The bench directory in the container is the working directory, and we want the current directory to have these YAML files available. Okay, so we are in the container right now, and we start with looking at the first benchmark. Oops, that's wrong, of course. This is the way we look at the first benchmark. So, for example, we have logging deactivated. Here's our main query, which is like filter, sliding window, and then we sum group by like the user ID, group by the campaign ID, and as our data input we have the YSB, which is let's say a hint to our benchmarking framework to use the internal magic Yahoo streaming benchmark data generator. So we don't read from a file or somewhere elsewhere, but we have an internal data generator. And here is some tuning parameters for the system. And down here we have the values that we want to, let's say, work on. So we have, for this configuration parameter, we give different values, and it will start runs for each one of them. We will just show how this looks like. So when we run as bench, it first complains that we should please give it a file, which we will now just do. So actually it gives a small warning, but this is just let's say, testament to the fact that it's a little bit work in progress. Now the data generator ran and generated pre-generated buffers. So because we want to benchmark the core engine, and we already finished the first run. We have 3 runs because we have these 3 variables up here for like Nautilus backend. So we already ran these 2 right now, and now the interpreter run is running. It's collecting a benchmark, a measurement every single second. And now we have our result CSV file. To look at the CSV file, we let's make this a little bigger. We have here some R code. We use the tidyverse, and then we look at our results, which we can see here, the tuples per second, and for the different Nautilus backends, which are query compilation backends. And we see that the MLR backend is a good bit faster than the CPP backend, which is much faster than the interpreter. Note that we will look at throughput here. The interpreter has good latency, and this is like this Nautilus research is from this paper, Query Compilation Without Regrets, from Grulich et al., where we have this framework of a just-in-time compiler with an IR where we have this MLIR backend. And let's see. And here we have like this query execution plan, and we either take the operator pipeline and interpret it in the interpreter, which is why it is slow, or it is first traced and then compiled to one of the multiple backends. And here we also benchmark the MLIR and the C++ backend. Yes, and those are then much faster. They are also hypothetically other backends, but we didn't highlight them right now. Okay, next up we want to show a little bit more under the hood how this works. For this we just started a quick run, because Nautilus is a query compiler, and as you saw here we have this step that after the pipeline we have this tracing step and then the code generation. And for this we have a small run, let's see, where we actually enable the where we tell the query compiler to dump its output. And okay, and now we just go into the directory where the dumped output is, and let's see. I'll actually just open it on my own machine, not in the Docker container. And here we have like the current output. The date is wrong. No, the date is not wrong. Actually, it's here. Yeah, here we have the output, and this is like the initial trace, where we see this is quite high level-ish with add and load instructions, etc. And then we have this more concrete trace, from which then an IR is generated, which is still like this NebulaStream IR. That is then compiled or transpiled to MLIR, which is then transpiled to LLVM IR, which is then finally compiled to binary. Yes, and so this is like how this compilation process can be traced and how it works under the hood in some sense. Yes, and next up we have another benchmark. This time we look at the pipelining strategy. I'll just start the benchmark. And with the pipelining strategy, this is an idea that was presented by Neumann, so not from TU Berlin, but from TU Munich, with this idea of merging operators. So we have hypothetically we have an operator pipeline, and they actually say, okay, wait until there's like a pipeline breaking operation, for example, building of a hash table or querying a hash table. Like everything can be like one big hot loop in some sense. Like this is on the right hand side here we have these things that we have these different, that we only like break a pipeline when we either materialize or aggregate, and besides this everything is like merged together or fused together. So we have this run now, and in the run we once run it with this fusion enabled, and once we treat every operator separately. So with fusion we just take, if we are allowed to, we merge operators together. And for this, let's see, we can see that operator fusion is in our current smallish example already quite a bit faster. And note that this is not that big of a query, so with bigger queries this might be much faster again. Okay, last but not least, we have a window strategy, which we want to highlight with its impact on performance. Again, I'll just start the benchmark run. This is a paper by Traub, Krulich et al. From TU Berlin on window aggregations with stream slicing, where an efficient way can be used to reuse parts of the window. Yes, let's see if... Okay, so it's still running. Yes, which again gives let's let's see. So we can see that the slicing strategy is much more efficient than this default bucketing that would be like the version without the optimization. Yes, so finally we wrapping up. We have this guide on how to benchmark NebulaStream with some hints. We have this NebBench utility that takes these declarative files where you can specify like different parameters or different configurations on how you want to benchmark NebulaStream. We have this Docker image that you can use to just try it out quickly. And yeah, this is roughly what we presented at DEBS, and we hope that you liked it. Thanks for watching.